hypervisor verification for CPU and SoC. He's the CEO of Breker, the leader in test suite synthesis and SystemVIPs. Previously, Dave served as VP of Worldwide Marketing Solutions at formal verification provider OneSpin. Earlier, Dave was president and CEO of Sigmatics, Inc. Is that right? Sigmatics. It says Sigmatics here. Sigmatics, sorry. Sigmatics. Anyway, that's history. As long as I get Breker right. Baker. He worked in sales and marketing at Cadence. That's an easy one. I was responsible for Verilog and VHDL verification product lines. As VP at Co-Design Automation and Synopsys, Dave oversaw the successful introduction and growth of SystemViPs before running marketing for Novas Software, noted for the Verdi product line, which became Springsoft and is now part of Synopsys. Dave holds a bachelor's, a BSc in Electronic Computer Systems from Salford University and an MSc in Microelectronics from Brunel University, both in the UK, and an MBA from Boston. Okay, there's a triple.
Thank you, Mike.
Master. Okay, over to Dave. Thank you.
Okay, long introduction. Sorry. Afternoon, everyone. So what we would like to do is go through, hopefully abbreviate 20 minutes, right, Mike? Yeah. 20 minutes, I guess. So go through a workshop that was put together by our CTO, some of you might know, Adnan Hamid, to talk about a real-life example, and actually picking up from where Tobias left off there, nice presentation, Tobias, looking at MMU verification. And of course, you know, RISC-V is very topical and very relevant these days, so we're going to go for an example using the RISC-V instruction set of this technology. And at the very end, you know, sort of show how we can synthesize some of these tests. So this whole thing is like an hour and a quarter long. I'm not going to go through that. I'm going to do the highlights like 20 minutes or so, hopefully. But if you want to see the whole thing, you know, grab a couple of beers. It's on our website. It's all video, maybe something stronger than a couple of beers for this one. You know, feel free to watch the whole thing. And Adnan gets into tons of detail on MMUs and hypervisors and all this exciting stuff. Okay, so quickly, what I'm going to try and go through is, you know, why on earth do we need these MMUs, memory management units? You know, how do they work? How the RISC-V ISA handles them? How we might produce a test plan for this? The test cases that we can come up with, and then how we can actually execute them and debug and so on. So why do we need MMUs? Well, there's a lot of reasons, but there's really three major reasons that I'm sure all of you are pretty familiar with. One is, you know, software basically needs more memory than is actually physically available, so you need to cache program data. Fragmentation is a big issue for memory, of course. Different processors will be basically using different parts of the memory and end up with memory blocks all over the physical memory, so you have to handle that. And something that's becoming more and more important as we get more aware of security is the idea of isolating blocks of memory with different processors and making sure that some processors can't read into other blocks. And how does this actually work? Well, we use virtual memory mapping, of course. So basically, we take the physical memory and the physical memory address, and we map a virtual address to that physical memory. Like this, basically. And to do this, we use basically a table. So we take the virtual address and map it through to a table system and then generate the physical address, be it in the RAM, the RAM, on disk, the cache, wherever it may be in the whole memory structure. And addressing cache is often used to do this, certainly is in RISC-V situation, where the CPU can send the virtual address to a cache, look it up in a table system, translate it to the physical address. All easy so far, right? So how does this look in the RISC-V world, and actually in a number of different CPUs? Well, firstly, we can't do this in software, right? If we tried to go through all these table entries in software, excuse the red thing moving around, I think someone left a bit of video in there. So we can't do this in software. It has to be done in hardware because of performance and power reasons. So in the CPU basically has the structures to actually handle all this and use the memory management unit to actually handle these tables. So if you look at the virtual address on the left-hand side here, actually, excuse me, start with this one. Basically, what we do is we have the virtual address that has a set of levels that access pointers into a table, a page table. The pointers then point to the base of the next page table. You go up to the address there, point to the base of the next page table, and then eventually end up at the physical address. Okay, with an offset so you have the base of the physical address and then an offset to actually access the memory itself, the actual address, the specific address. So this, works pretty well. There's a few other requirements. There's a number of flags that you have to put on the address as well, as you can see on the bottom there. And basically, you can end up pretty rapidly with your physical address. This is a one-stage translation, address translation. And that's interesting, but quite often these days, we're worried about virtual machines and two-stage address translations. So in this example, you think of a situation where you're running, say, Windows as a base operating system, and then you've got a hypervisor and a virtual environment that has, say, Linux running on Windows. So the Windows address system would be on the right-hand side here. You'd have the same virtual address system we just went through for that. But then this reads in a guessed physical address from the virtual machine in the operating system that doesn't even know it's running on another operating system, right? So then you have the whole separate page table walking in the guest system, which would be sort of Linux in my example. So there's a lot of processing here and a lot of things that can go wrong. And the question is, how can we reliably verify all this is operating correctly? The memory ordering issues that Tobias correctly mentioned are being handled properly, that all the addresses are properly set up, that the caches are being flushed properly when we actually swap in and out different address tables, and so on and so on and so on. Quick look at the RISC-V spec. Now, I wonder how many of you have actually had the joy of reading the RISC-V ISA spec. I won't ask for a show of hands, but I'm sure some of you have. I know you have. I know Simon has up there. So the RISC-V spec it's a pretty comprehensive document, well written, but what you'll find is much like a fragmented memory situation, here we have a fragmented spec, where you have major parts of the specification in one area, and then you have to jump to another area of the spec, another area of the spec. And if you look through all the instructions, the RISC-V instructions in this spec to handle all this paging, you end up with a whole bunch of different pages and information here. Note some of this is in blue. I'm not going to start reading it, but you get a sense that it's complex stuff. There's some here relates to the page table entries. By the way, when Adnan does this, he actually reads part of it out, so you save that. And some of it relates to the virtual address translation here. So what we need to do is take this spec and create a verification plan, and then create keeps jumping, and then create actual tests and a coverage model based on that. And this is what we want to go through in this example. So what does a test plan look like? So what I want to do is step through just a part of this verification plan that we make use of within the Breker technology to actually do some of this testing. It's jumping. So the first thing we want to do in RISC-V is select what they call a privilege level. So a number of different privilege levels, user modes, and so on, which we want to set up correctly so so that we can do the memory management operations that we need to. Here, what we'll do is select first the user privilege mode. You have like a graph type nomenclature here where you can make a decision. That's that little purple box, and then these blue boxes, which are actual operations. We're going to go to the privilege user mode. Then we're going to set up the one-stage address translation, set the right flags to do that, and select an operation within that. From there, we're going to go and set up a specific paging mode. So there's another set of graph-based operations here to do that. We basically set the paging mode. We set the code stack and the address size, that page table system that we just went through, and sort of build all this up inside this graph nomenclature again. Also notice that there's a decision box on the right-hand side, that little purple square, and that can be set up to use random decisions to actually move between different operations depending on what we want to do. And what we want to do is choose different operations here. So what we want to do is select either a load operation, a store operation, an execute operation. I don't know why this is jumping, but I don't. So to do this, we run through a different set of operations. We make a decision. This decision box can be randomized. And essentially what we're able to do is execute the right instructions, the fence instructions, the right load, the store instructions, whatever it is, inside the test plan to execute one of these operations. Here we're going to do a store operation. So we set up the flags. We set up the virtual address and set up the different paging operations and basically create that address. We allocate the virtual address in that page table that we talked about before, and generate the fence instructions that basically protect the memory ordering of this test. And so finally, we then map the physical to the virtual address in that, the physical to virtual address in that table, as we went through before. And this could be done, based on the way the tables are structured and set up. One thing that complicates, obviously, this kind of test for MMU testing is every time you run these instructions, you're getting a different memory format. So you have to sort of stay on top of how the memory is behaving. And if we want to include checks in these tests, which we do, we have to be calculating the memory operations as we run through this. So you end up, and finally we have to set up those PTE flags that we discussed as well at the beginning. So we want to set some of those. So we end up with something like this, a very large graph, which looks pretty complicated, but it isn't so complicated because it's broken down into the blocks that I mentioned. I can select them all here. So basically, this is a fairly complete graph of a hypervisor MMU virtual test. And the way we operate this using synthesis technology underneath is we basically walk all these different paths through this graph, make random decisions in these different purple boxes, and end up with a whole broad range of tests. If we actually executed all the paths, you end up with a huge number of possible tests. So we actually use, in fact, an AI technique, not an LLM technique, but an old expert system technique, to select the best paths through this different graph to make the right decisions to select a certain number of tests that would actually work to produce the right coverage that we want. The whole thing would be coverage directed, so we can use those planning algorithms based on the coverage mechanism. So we end up with this nice big graph. We can execute it, and we can drive these tests very simply. Some of the example test cases that we get out of doing this. This is the one-stage address, so no virtual machine here. This is just a straight OS running on the processor. You basically see that we have, we have the different modes being set up, the PTE being set at the pointer with the faults, and so on through this whole test. And if we go to a two-stage system, the test looks something like this, where you actually can walk through the tables, check the coverage built into the test, do the load, store, and branch instructions to and from the virtual addresses that have been set up, manage the sign extensions, and somewhere in there's a check as well. So this is actually what the test ends up being look like after you've walked this graph. Some of the bugs that we've found, these are actually all fairly recent as well, just in this particular piece of code, gives you a sense of the kind of awkward things that you see. Situations like memory ordering problems, page faults, issues with the hypervisors and so on and so on. So these are kind of awkward, complicated bugs that are hard to track down and generally representing sort of strange corner cases with multiple parts of that graph coming together to actually sort of create a corner case condition that's tricky. Debugging, Breker has a debugging technology that looks like this. It's multi-threaded, so we can actually track the operations through the different threads. And you can see a failing task, actually find out what addresses and information around the task is creating the failure. Look at the failing error itself and even check the ID in the original code. So we have a fairly sort of high-level way of looking at the system code, which then you can bring up something like Verdi and do the signal debugging that you need to do. And for coverage, what we actually do is flatten that whole graph into a tree-like structure like this and then test the coverage across it. So this is not functional coverage. This is like scenario coverage, if you like. We're actually doing the coverage of the original test. So you get a graph that looks like this. And the red stuff is things that haven't been covered at this point. Obviously, the other ones have been covered either once or many times. And to go back to that spec with some of the blue writing on the left, what we actually ended up doing right now is frankly manually going through the ISA spec and creating a verification plan for all these different system VIPs that we've created, including the hypervisor and the IOMMU testing. And that then drives the coverage model. So this is a fairly reasonable translation from the verification plan to scenario coverage. Now, the interesting thing is we've been talking about AI quite a bit, and one thing that Breker is looking at and working with some of the AI companies that are emerging now is automating this process from spec to the coverage model. And that would be very interesting because, as I said, this spec is one of the more complicated ones out there, and being able to automate this process would, of course, be huge. A table of all the things we have. And then finally, a sense of the actual tools that Breker used to translate this graph. I'm nipping through it, Mike, don't worry. So system VIPs at the top, which include different tests like the RISC-V tests. Synthesis technology generates stimulus checks, coverage, and debug. Then we can generate UVM or software tests or combinations thereof, depending what we want to do. Apply it to different platforms, and then finally the debug operation. And that, I think, is it. Oh, thank you. Bang on time. That was lucky.
Okay. And that's also, I think we're working with David some compliance suites for RISC-V International, which is going to be hopefully sometime this year.
We'll see.
We'll see.
Yeah, that's a long story.
So there's a big board involved, so it takes a long time to make any decisions from RISC-V International.
But I would just quickly say, if you do want to see this whole presentation videoed with a lot of in-depth information on IOMMU verification, it is up on our website, and I can put it on yours as well.
Yeah, you can send us a link. We've got our newsletter going next week, and I think as a gold sponsor, you get a follow-up email as well. So
excellent. That's nice.
So these good people will probably receive free emails from me. There you are.
Great. Thank you.
So there's no chance they'll miss it.